In this video, we will talk about the general definition of unitary operations, which describe multi-qubit circuits, and highlight some of the most common 2-qubit gates utilized to construct these circuits. Let's recall that any single qubit operation is described by a matrix, let's call it U, of the form U00, U01, U10, U11, where we said that U is a unitary operation. And what we mean by this is that when we multiply U with this conjugate transpose, we get the identity. In other words, U is an operation that involves a state such that there is another operation that we call U dagger that when we apply it right after applying U, reverses the state to its original value. Therefore, multiplying these two operations is like applying an identity. And the reason we said that qubit operations must be unitary is because they are not just reversible, but also norm preserving, meaning that if we start with a normalized state, after applying U, we end up also with a normalized state. Now we can generalize this for multiple qubits by saying that if we have an n-qubit system, any operation can be described by a unitary U of the following form, where here this capital N is equal to 2 to the n, and as we said, this lowercase n is the number of qubits in our system. Now this matrix U also meets the condition that when we apply this conjugate transpose, we get the identity. And just as a reminder, the conjugate transpose is found by taking the transpose of the matrix and then replacing each element with its complex conjugate. So for example, in the case of one qubit, this U dagger is given by U00, U11, so the diagonal terms remain the same, and then we exchange the off-diagonal terms. So here we have U01, U10, and then we take the complex conjugate of each of the elements. Now we can construct multi-qubit unitaries from single-qubit unitaries by using the tensor product. So for example, if we have a circuit with, let's say, a unitary U0 on qubit 0, unitary U1 on qubit 1, all the way down to a unitary n-1 on qubit n-1, the total unitary for this circuit will be given by the Kronecker product of the individual unitaries. So let's take a look at an example of this in Qiskit. So here we're going to import NumPy, and from Qiskit the quantum circuit class, and from Qiskit quantum info the operator class. And let's say we want to create the following circuit where we're applying an H gate to qubit 1 and an X gate to qubit 0. And let's go ahead and draw that. So to find the total unitary for this circuit, what we can do is use this operator class, pass the quantum circuit, and then we can draw it. And here we have the total unitary. But let's see if this matches what we described before, which is that we should be able to construct this matrix by taking the Kronecker product of the H gate with this X gate. So let's define the X matrix using the operator class and this from label function. And same for the Hadamard matrix. And then we can use from NumPy the Kronecker function and pass the Hadamard gate followed by the X gate and store that in a variable, let's call it hx. Now this NumPy function will return a NumPy array, but we can pass that to the operator class to turn it into a qiskit operator, which we should be able to display. And here we have it, and we can see that the two matrices match exactly. Now, of course, we can generalize this for more qubits. So we could, for example, turn this into a 3-qubit circuit and now apply, let's say, a Z gate to qubit 2 and do the exact same thing. Define now a matrix for Z and then add the Kronecker product between what we had before and this Z gate. And as expected, these two matrices match. Now, one thing I just realized from this Qiskit exercise is that this definition I have here has a small mistake, and is that this index here should actually be n minus I, where I is going from actually 1 to n. And the reason for this is because we've said in the past that the way we organize our qubits is by placing the most significant qubit to the left of our state. So qubit n-1 goes first, then qubit n-2, and then all the way down to qubit 1 and qubit 0, which means that our unitary operations should be organized with the one acting on qubit n-1 first. So that way, when we start with I equal to 1, the first one we get is u of n-1, then tensor with u n-2, and then all the way down to u of I equal to n, which will make n-n equal to 0. And the other thing is that we also like to keep the convention where we have the most significant qubit at the top of our circuits and the least significant qubit at the bottom. And this is just to adhere to the most popular convention that you will find in most popular textbooks. Now, multi-qubit unitaries composed of single-gate unitaries are very important, but they really constitute a very small fraction of all possible unitaries. More generally, we can have a unitary U that takes as an input n qubits and cannot be expressed as a tensor product of single-gate unitaries. A clear example of this is an operation we're very familiar with, which is the CX gate. The CX gate is a 2-qubit operation with the following matrix, which can be shown that cannot be implemented by taking the tensor product of two separate unitaries, U1 and U0. Instead, the CX gate is part of a bigger family of gates known as controlled unitaries, which we can actually represent in a very interesting way. So let's take again the CX gate as an example that we know acts on 2 qubits. And we can actually express it in the following form, where we have the outer product of state 0 with itself tensored with the identity matrix, plus the outer product of state 1 with itself tensored with the X matrix. And the reason this expression works is because let's take a look and see what happens if we apply the CX gate to state 0, 0. So in this particular case, we have the outer product of 0 with itself acting on this qubit to the left, which again is state 0, tensored with the identity on qubit 0, plus the outer product of 1 acting on state 0. So again, this is the first qubit, tensored with X acting on 0, which that's for the second qubit, right? So we know here that this corresponds to the inner product of 0 with itself, which is equal to 1. So for this portion, we just get state 0 tensored with the identity acting on 0, so that's state 0. Plus, here now we have the inner product of 1 with 0, which we know is 0. So this whole term here is just 0. So this showed that applying the CX gate to state 0, 0 just gives us state 0, 0 as expected for the CX gate. And we can repeat this for 0, 1, 1, 0, and 1, 1 and see that we get the correct operation. Let's do it actually on state 1, 1, which is a little more interesting. In this particular case, this inner product of 0 with 1, which is 0, so this whole term cancels. And then here we have inner product of 1 with self is 1, which gives us state 1 tensored with the X gate applied on state 1, which is state 0. So this gives us state 1 tensored state 0, which as we can see is the correct operation for the CX gate because we have the control qubit in state 1 and the target qubit in state 1. And what we've seen here is that this operation has correctly flipped to state 0. And the idea of expressing this CX operation like this is because then we can generalize this for any type of gate. So we can define any control unitary as the outer product of 0 with itself tensored with identity. And if it's not clear yet, what this means is that when we have our control qubit in state 0, we're going to apply the identity plus the outer product of 1 with itself tensored with U, which means that if the control is in state 1, we will apply to target the unitary U. Now, sometimes you will see that for this outer product matrices, so let's recall that this outer product of 0 with itself will result in the matrix 1 0 0 0, and for 1 is the matrix 0 0 0 1. Sometimes I'll write them down as pi 0 and pi 1. This is just convention for what are known as projection operators, and pi is just the conventional label used for them. So with this, let's take a look at an example. Let's say, for example, we have a control Z gate, which will be pi 0 identity plus pi 1 Z gate. We can construct the matrix corresponding to this operation by just replacing each of these elements with their corresponding matrices. And what we'll find is that we get the matrix 1, 1, 1 minus 1 in the diagonals, and then the rest of the elements are 0, which corresponds to an operation that basically says that for states 0, 0, 0, 1, and 1, 0, our state remains unchanged, but for state 1, 1, we add a phase of -1 to our state. So let's take a look at this example in Qiskit, and let's construct a circuit with a ZZ gate and compare it with what we get out of this expression. So let's define a quantum circuit with 2 qubits. Let's apply a control C gate between qubit 1 and 0. Let's go ahead and draw that. And if we look at the operator for this by passing that circuit and display it using LaTeX, we can see that we have that diagonal matrix with only the last element being equal to -1. What this means is that if we were to apply an equal superposition state at the input of this gate, all states will remain with the same phase except for state 1, 1. We could take a look at that by applying those Hallamar gates and looking at the state vector at the output. So let's import from Qiskit Quantum Info the state vector class, and let's look at the state vector at the output of that circuit. And we see here that we get the equal superposition state, but where the last state has a phase of -1. And now let's take a look and see if this matrix, which was only for that CC gate, matches what we get out of the expression that we used to construct it. So let's define the matrix for our identity using the operator class and the from label function. We already defined the matrix for the Z gate, but let's do it again just for completeness. And then we can create the pi 0 and pi 1 operators also using this from label function and just passing the label 0, and same for 1. And then we can say, okay, a CZ gate consists of the Kronecker product of pi 0 with the identity plus the Kronecker product of pi 1, the Z gate. And recall this Kronecker product function is going to return an array. So let's just turn that into an operator object so we can display it using the draw method. And here we can see that we get the exact same matrix we had before. Another nice thing about this definition for control gates is that we can play around with it a little bit to create, for example, a gate that applies a unitary, let's say for example the X gate, to a target qubit when the control is in state 0 instead of state 1. So let's call this a CX gate, but with the control reversed. And the way we do this is, well, now we take the outer product of state 1 tensor with identity. So if the control is 1, we will apply identity. And a control of 0 tensor with the X gate. And this will be equivalent to an X gate where the way the control qubit works is reversed. And we can of course generalize this for gates with more than one control. For example, we can create a gate with 2 control qubits where when the first control is 1 and the second control is 0, activates an X gate. And the way this will work is, well, that X gate on the target qubit only gets activated when we have state 1, 0. So we have to tensor that with the outer product of that state. And then for all other possible combinations of these 2 controls, we need to tensor them with an identity. So if we have state 0, 0, or state 0, 1, or state 1, 1, we apply an identity. So let's now take a look and see how we do this in Qiskit. So let's first explore the case for where we have a CX gate, but where we want to flip the target qubit when the control qubit is 0. So we still use the CX operation, and we're going to apply it between qubits 1 and 0. But here we can pass as a parameter this control state and set it to 0. And if we draw that circuit, we see that now we have this X gate where the control is an empty circle instead of a filled circle. And that's just to indicate that this will activate this gate when this qubit is 0. And we can take a look at its corresponding matrix by using the operator class. And here we have it. We see that this is a matrix that when we input state 0, 0, it will output state 0, 1. If we input 0, 1, it will output 0, 0. And states 1, 0 and 1, 1 remain unchanged. And as before, we can generalize this for more control qubits. Now, if we wanted to apply this to a gate that is not an X gate, what we have to do is first import that gate from the qiskit circuit library. So let's take as an example a phase gate. So let's do from qiskit circuit library, import phase gate. And what we can do is create, let's say, a multi-control phase gate by creating a phase gate object and then using the control method to specify how many control qubits we want and the control state. So here we can say we want to have 3 control qubits with a control state 0, 1, 0. So this means that that phase gate will be applied to a target qubit when the control qubits are in state 0, 1, 0. Then we can create a quantum circuit that's going to have 4 qubits because we want 3 qubits for the control and 1 qubit for the target. And then we can append this gate to qubits, let's say 3, 2, 1, and 0. And since the phase gate takes as a parameter some angle that we want to apply, we also need to specify that here. So let's say we want to apply an angle of pi over 2. And that would give us this phase gate that when the control is 0, 1, 0 would apply a phase of pi over 2. And we can do this for any other gate. So for example, we could do it for a Y gate and we can create our multi-control Y gate. Here we won't pass an angle because the Y gate doesn't take any parameters. But again, we can say it has 3 controls and maybe it gets activated when we have state 1, 1, 0. And then we can append it in the same way. And now here we have a multi-control phase gate and a multi-control Y gate with different controls. And the order in which we append these qubits specifies where our target goes. So the last qubit is always reserved for the target. So if we wanted, for example, the target to be qubit 2, what we could do is change this order and do here 1, 0, and then the target on qubit 2. And that would have that Y gate being applied on qubit 2 when qubits 3, 1, and 0 are in state 1, 1, 0. Now, one last gate worth mentioning before wrapping up this video is what is known as the SWAP gate. So the SWAP gate does exactly what the name implies. So it swaps the state of 2 qubits. So if we have state 0, 0, well, we will get 0, 0. If we have 0, 1, then the SWAP gate will swap the bits. So we will get state 1, 0. If we have 1, 0, then that swaps to state 0, 1. And then 1, 1, of course, results in state 1, 1. The symbol for the swap gate is as follows. It has 2 X's on each of the qubit lines and a line connecting them. And we can construct the matrix corresponding to the swap gate from this correspondence. So this maps state 0, 0 to state 0, 0. Here we map state 0, 1 to state 1, 0. And then state 1, 0 to state 0, 1. And lastly, state 1, 1 remains unchanged. And of course, there's also a controlled version of the swap gate, since we can control any type of gate. But this gate is important enough that it has its own name. It's sometimes referred to as the Fredkin gate, and its symbol is basically same as the swap gate, but with an extra control qubit. Now, of course, we've talked about how to construct all these different gates, but if we wanted to get the unitary for a circuit composed of several single qubit, 2 qubit and 3 qubit gates. Well, let's take a look at an example. What we do is we follow the same procedure we've described before. So we can break this into different sections and say that before that control X gate, what we have is for the most significant qubit a Hadamard tensored with identity and another identity for the other 2 qubits. And then we multiply this with what's next. But remember, since this matrix is going to be acting on a state on the right, the next operation to the right on the circuit is going to be on the left of the matrix multiplication. So here we have a CX gate, which is a 2-qubit gate, tensored with an identity. And lastly, we have this control Z gate, which is actually acting between qubit 0 and qubit 2, but is leaving qubit 1 idle. So we need to come up with a unitary matrix for that. And the way we do this is by using that definition we had for control gates, where for a control Z gate, we had pi 0 tensored identity plus pi 1 tensored with a Z gate. But notice that this is acting on qubit 2 and this on qubit 0, and we're doing nothing on qubit 1. So what we need to do is insert in between these tensor products another identity. So we can just move this and add another tensor product with identity, and say here at the end we add identity and a tensor product with a Z gate. And let's call this unitary, I don't know, K. So then what we do is we will multiply here by K to get the total unitary for this circuit. So that's it for this video. As always, let me know if you have any questions, and hope to see you in the next one.